PhD both in Sao Paulo and in Bordeaux in France, and he had to make two versions of his defense, one in Portuguese and one in French. In 2011 he went to the University of Lisbon, where he works in astronomy and particularly in the development and application of innovative methodologies for the study of our universe. Since 2006 he's working on Gaia and in many different fields of the Gaia project. One where there is a big connection also with our group in the area in Heidelberg is that he's working in visualization, where we are also doing work on, and so we are collaborating on this. And he's also doing work for the industry, for instance, finding what the best reference frame is for new star trackers on satellites with a much higher accuracy as the current star trackers used on board of satellites or probes, which are responsible to get the right attitude of a satellite. But today, this talk is on the fourth paradigm of science and astronomy, and we are looking forward to your talk.
Okay. Thank you, Stefan. Thank you, Stefan, for the nice introduction. Also, thank you, Elena and the Heidelberg Joint Astronomy Colloquium for the invitation to be here today. Well, guten Tag. So, today we're going to talk a little bit about the fourth paradigm of science and mainly of how it emerges inside astronomy. But before talking about this so-called fourth paradigm, I just wanted to go a little bit back on time, just to put things into context, and to talk a little bit about what this wise Frenchman that perhaps most of you recognize, the idea that he had about astronomy. So he believed that it was astronomy who made us as so capable of understanding the nature. And why was that? Because it was astronomy to him that taught us that there are laws in the universe and the regularity in the universe. And well, if his idea of astronomy is correct or not, perhaps we will never know. But something that we can know already is that the oldest, the ancient representations of regularity made by humankind are astronomical. So at the same time that humankind were starting to create anthropomorphic representations of ourselves, so the gods from the Aurignacian culture, we also started to chart astronomical events like the phases of the moon and the position, even the position of the moon along time. And so there is a correlation. This does not imply causation, obviously, but there is at least a correlation between the things. But what we can know, however, is that along the entire development of human history, astronomy has always been connected to the several developments in technology, and in many cases, astronomy also served as the driver for the development of the technology. And in mathematics, we can see that a lot, for instance, with problems with Poincaré and Laplace in celestial mechanics or Newton with gravity. And nowadays, this is not different. And here is where the so-called fourth paradigm appears. But what is the fourth paradigm? To answer this question, I will borrow a slide from the creator of this concept. That is this researcher. He's a researcher in computer science. He is a Turing Prize in computer science. His name is Jim Gray, and he worked for Microsoft Research. And for us, astronomers, he was very important, even if we don't know him. Because it's because of him, and also because of Alex Allais, that Sloan came to be by the time that Sloan came to be. Without the researchers from these two researchers, especially in the area, in the field of databases, we would not have Sloan 15 years ago. We will probably perhaps have Sloan 5 years later or 10 years later. And And so they created this concept of the fourth paradigm, and to them, the idea is that science changes along time, and the way we do science changes along time. And the idea of the fourth paradigm is that in the beginning, we were creating science, science was developing by empirism, so we were only trying to describe a natural phenomenon. Afterwards, we started to generalize and create theories, so it was a theoretical science. So this would be the second paradigm. We would create models, generalizations of things, and then try to explain nature. In the last few decades, we started to see another type of paradigm that is the complexity of these theories is so huge that we started to being enabled to write them analytically. So we started to simulate complex phenomena, and this is the idea of the emergence of the third paradigm. And the fourth paradigm, it's what we call data-intensive science, or in the markets, people used to call it big data, things like that. But the idea is that you unify theory, experiment, and simulation, and the link between everything is data. Data, observational data, data simulated data. But the link between everything is data. And in fact, when we look to the process of generation of knowledge, be it from observation to publications, or from theory to publications, we have data everywhere. The observation that produces raw data that goes to the data, that produces reduced data, or the theory that produces calculations that reproduces simulated data, and then everything is joined into an analysis that goes to catalogs, tables, and everything ends as publication. It's also data in some sort, right? It's not yet computer graspable data, but it's already data. Not yet computer graspable data. So basically, this fourth paradigm emerges in astronomy as these three disciplines of space, astroinformatics, statistics, and the virtual observatory concepts. So this is how in astronomy, inside astronomy, this concept of the fourth paradigm is emerging. And it's emerging naturally. It's not that someone's bringing it. It started emerging by itself. So if anyone wants to go deeper into the concepts and the basis of this idea of the fourth paradigm, there is this book that was published by Microsoft Research when Jim Graves appeared. He's the seasoned pro. He's appeared in the sailboat some years ago, and to honor him, Microsoft published this book. And well, it's free. You can download it for free on the internet, or you can download it as well. So that was for the first part of the talk. And the second part of the talk, I will present you three examples of how this fourth paradigm appeared in my research work, my recent research work. So in the first example, I will show you how we can create models and teach the computer something. So this is a little bit more traditional way of doing computational science. In the second, I will show you how we can let the computer create the models of the universe itself. We try to start and trust the machine with another step in the discovery. And in the third one, the idea is that we're going to try to forget about complex model or things that we write, and we will worry only about the results or the solutions of a problem that we have. Why is that? Because when we were creating the model, when the computer is creating the model, depending on the model that you create, you always introduce biases in your interpretations. You can get rid of bias, you can try to get rid of that, but it's even better if you let the machine emerge with some solution by itself. So, for the first example, so try to create the model. So basically, the idea here is that the Gaia satellite, perhaps many of you know, have heard talks about Gaia already here in the Institute. The Gaia satellite, it's an enormous mission, but it was created to study point sources, only point sources. Everything that's non-point source, non-point-like, even the data transfer itself tries to block on board of the satellite. And The problem is that Gaia it's out there and it's observing everything that's in the sky, including many, many galaxies. And many galaxies which will not be observable that are not observable, at least the structure of them from the Earth. And we had this question, is it even possible to extract morphological information from these galaxies that are being observed by Gaia or not? In the beginning, we didn't. So the idea is that since Gaia was designed to observe only point sources, and its observational strategy and data transfer prioritization is unfriendly with extended objects. However, they are scientifically interesting objects because all of those objects have a radii smaller than 2 arc seconds. So from Earth observatories, it's very hard to get any kind of morphological information. Obviously, you can get morphological information for 1 or 10 or 100. Perhaps if you're very lucky with your application to the VLT or the ELT, or with 1,000 objects like those. But you're not going to get 1 million or 10 millions of those objects. For that kind of study, you need to go to space. And different from other space missions, Gaia will observe them all over the sphere, so it's in the entire space, in the entire sky. You don't have pointed regions. You have them all over, spread all over the space. So the solution that we proposed and that was accepted is that we are not going to try to inverse the problem. We're not going to try to look at the Gaia data and after looking to the Gaia data, trying to inverse and then to analyze the inverse problem. What the solution that we try to do is to do forward modeling. So you start from a model of the universe and a model of how Gaia observes the universe, and you try to simulate the Gaia data and to compare the simulations of Gaia data with the observations. So you don't try, for instance, to solve an optimization problem to inverse, generic optimization problem to inverse the data, but you try to forward something that you believe already or some type of model that you believe already that your reality is. But to do this type of thing, you need to have a forward model. So you need to construct a model of your universe. The model that we built for Gaia was, first, well, what's a galaxy? You can put anything inside, but the most basic thing, it would be an exponential disk and a surface approach. But you can add other components here too if you want. From this, you create synthetic images of the galaxy in the focal plane. After that, you convolve with Gaia's PSF, and then you add something that's very important, that's the charge distortion. And luckily for us, there is a mathematical transform that does to a signal exactly what Gaia does during the observational process. Because what Gaia does during the observational process? So, supposing that this is a star. When Gaia observes a star, it integrates the signal in different angles. So it will integrate the signal in this direction, or in this direction, or in this direction. So you have one observation that's like this, another that's like that, and another that's like that. For a point source, this is no problem because all the integrals will be the same. But from the moment that you have a galaxy, depending on the angle, you have different integrals. And the nice thing is that this transform that's called Hadron transform, this is the mathematical description of exactly this process that Gaia is performing. And when we go to the hospital and do a tomography, in many of the tomographers, what they do is just an inverse Hadron transform. So Gaia does not observe all the angles, so it's not homogeneously covered. So we need to select at least all those angles and in which Gaia is observing. So this is basically two examples of a galaxy. So it's a bulge plus a disk, as observed by Gaia. So in this direction, in the x direction, you have the angle of the observation, and in the y direction, you have the distance from the center of the object of a certain pixel. So this is the sky mapper data, so it's Gaia low resolution data. It's low resolution, but you have 4 arc cycles around the center of your objects of data, and this is the high resolution data, so you have 800 milliarc cycles of pixels, of integrated pixels. We call that samples. Well, basically, as you can see, the bulge and the disk is the most external part of the galaxy. And once you have a forward model of what's happened during the observational process, you need to optimize. You can use anything to optimize, but a good way to optimize this type of data is to use a local optimizer and a global optimizer. A global optimizer to find the region where the optimal parameter is, and then you just use a local optimizer to accelerate the convergence. What we can do with that? So these are some examples of simulations. We can perform, for instance, image reconstruction for all the objects observed by Gaia. Gaia does not create images, but using this type of thing, we can reconstruct images. We can perform purely morphological classification. Gaia will perform spectral and spectrophotometric morphological classification. But this is purely based on morphology. So using this information and the spectral classification, we can check if there are anomalies between the types of galaxies that we observe. And obviously the most interesting thing is that you can perform parameter determination directly from the Gaia raw data, it's really raw data, and not from reconstructed images, because when you inverse and reconstruct and then analyze the reconstruction, you're poisoned by several reconstruction artifacts. In this type of solution, you don't have reconstruction artifacts. So this is just an example that shows that for the intensity of the disk of the galaxy and the radii, or the radius of the disk of the galaxy, we are under 5% error. Today, this is old data, the old simulations. Today we are around 10 to 20% of the size of the galaxy in the errors, depending on the radiation damage history of the satellite, for 15 parameters. So the positions, we fit the right ascension and declination for all the objects that we treat, and the position angle, the disk, the intensities, the radii, the bulginess or diskness, like that. But those were simulations. What about real data? I cannot tell you because I don't know neither. One thing, guys, that our software, the software that we write, they are processing data, but we cannot see the results of data. We are going to see the results of most of the things at the same time that you are going to see it. But something that I can tell you already that Gaia is observing galaxies, and they are being treated. Each black point here in this map, so this is a position map, each black point is a zone, it's a galaxy from the SDSS, from the zone neutron sky survey. Each red circle marks the detection of that galaxy by Gaia. So, for the galaxies of this zone neutron sky survey, that Gaia can also observe because of the magnitude range. Most of them will be analyzed with space quality, especially for the morphological parameters. There are some consequences of that pipeline. One is that the determination of morphological parameters is okay, it's doable. But we have some byproducts of that. One of the byproducts is that we are going to analyze all the quasars that are observed during the mission to look for the signature of the host galaxy of the quasar. Why this is important? Because if the host galaxy, if we can even see some faint components for the host galaxy, you don't want that quasar to take part in the astrometric reference frame materialization. And so doing that type of analysis, we can avoid all the quasars for which we can see the host galaxy. And something that I personally think is really, really interesting is that using this type of solution, we can analyze quasars suffering gravitational lensing. Today, we know 100 of them. If our understanding of the cosmological model is correct, we should expect for the Gaia range, for the Gaia magnitude range, between 1,500 and 2,500 quasars. So that means that we are going to resolve, only because Gaia is in space, we are able to resolve the components of all those gravitational lenses. And this is some real data that I can show you already. This was made public some weeks ago in the picture of the region. So these are two quasar suffering gravitational lenses. This is the famous Einstein cross. So each black point is one Gaia observation, and the underlying image is an HST image. But these are very, very raw data from Gaia. This is not considering any type of fine astrometry for the reconstruction of the satellite attitude, for instance. And we are already at between 50 and 100 milliarc seconds receiving for all those detections. Okay, but that until now we were considering a situation where we know how to model the world. What if we don't know how to model the world? Well, now we enter into the second example. There is something that has been introduced by computer scientists some time ago. It's called symbolic regression. Historically, how we have been using computers. I think that most of us around here have been using computers to do numerical work, right? Or when we are using computers to do analytical work, is just to make some algebraic manipulations. But usually we don't entrust computer with more than simple algebraic manipulations. Symbolic regression is a method that is, as the name says, a regression using symbols. Just like we use to do regression, linear regression, we can also do regression using the symbols themselves. Basically, the idea is that from the data, we let the computer analyze the data and try to extract analytical representations that are inside that data set. And this is very interesting because up to very recently, this was a humankind only model. This is basically what Tycho and Kepler were doing, right? So one was getting data and the other one was looking to the data and trying to extract the mathematics behind the data. And this is a very interesting thing because Schmidt and Gibson in 2009, they published they published a description of a heuristic, in fact, of how we can let the computer do those things. Well, the idea basically is to collect first all the experimental data. Once you have your experimental data, you're going to compute numerical derivatives between pairs of variables inside your data. You select all the columns of your data, you compute the derivatives between them. You let the computer construct a very large group of possible equations, randomly, but simple equations. The computer will calculate the portion of the derivatives of the analytical representations, and will compare with the numerical derivatives of your data. Once it does that step, it will select a fraction of the good candidate equations, and it will iterate the system by combining to create more complex relations. So this is basically an evolutive algorithm. So it's just like a genetic algorithm, something like that. And after some time, it will converge into a series of equations that are inside, that can, in a certain way, compress your data. And one thing that's very interesting here is that as the comparison metric is not only how good the equation is to predict your data, but it's also how simple it is. So if you have two equations that are as good, one is as good as the other to predict your data, the method will select the simplest one to keep for the further generations. So this is basically like the knock-and-razor principle that's been applied inside here. So these researchers, they applied that method to several different types of mechanical systems. So pendulum, composed dumbbell pendulum, forced pendulum, spring systems. And the computer started to write in the Emergence the equations of motions, Hamiltonian of the system. And this is, so the system looks to work, but is it possible to apply it to something in astronomy? So together with some colleagues from MPA and CASI at that time, we tried that method into slower data to try to predict, to build an equation to predict photometric redshifts. And so our question was, is it possible to create, to write a very simple equation to predict photometric redshifts or not? Basically what we used to get a small fraction of the known data set, only 40,000 galaxies. We got the photometry for these galaxies and the spectroscopic redshift for these galaxies. We used the symbolic regression engine, it's called Alberto, using cloud computing in Amazon. And after the launch, we had a very nice and simple equation that contains very interesting thing. One, it's very compact. It's not like a very large polynomial fitting with hundreds of terms. And in this global, we entered all these global features, so U, G, R, I, Z. And the computer built an equation that did not consider U and Z. And there is a reason, a physical reason for that. Because for most of the galaxies inside the known, most of the galaxies inside the known are between redshift 0 and 1. And between redshift 0 and 1, the main feature to bring the redshift into the photometry does not cross the filters U and Z. That is the greater than 4,000 angstrom. So the computer discovered by itself that for those galaxies, redshifts between 0 and 1, the filter U and Z, they were not extremely important. So he preferred to keep an equation that was simpler than to keep a very big equation with all the terms, even if it would be a little bit better in the prediction capabilities. But does it work? So here, to test and to validate this method, we applied the equation to 1.4 million galaxies of this known, so all the other known galaxies that had photometric spectroscopic redshift method. And in this axis, you can see the photometric redshift, and in this axis, the spectroscopic redshift. So this is a very, very simple equation, but nonetheless, it managed to reproduce very well, at least visually, until now, very well the spectroscopic redshifts that were measured for those objects. And if we look into a violin plot, we can check for each redshift beam how are the error distributions of the equation of the method at each redshift beam as well. And we can see that for most of the range, so up to redshift 0.8, the equation has a very, very low error level. After redshift 0.8, the equation starts to lose the predictive capability. And why is that? Simply because you have more and more flux into the Z filter. And this equation does not take into account the Z filter. So the equation starts, the validity of the equation starts to break around this. But why the method didn't take that into account? Because in this redshift interval, there are very few slow galaxies. Most of the galaxies are around here. And you can see that in the marginal distribution. So this distribution is just the integral of all these other distributions in this. Well, this is just all the redshifts into a single distribution. Okay, but numerically, we can see also, well, this was a visual comparison, but numerically, we can also see that this equation is rather competitive with many other methods, like neural networks, that are cumbersome in some cases to interpret. To use it's okay, but the interpretation of those methods in certain cases is complex. And the bias and the scatter are at more or less at the same level as those much more complex methods. But this is not the point here. The point is that there is an equation if the computer could find an equation, probably we could use also an analytical equation for computing, for predicting photometric redshifts. It's just that there is a simple equation that the first thing to propose this equation was not a human, but it was a machine in the end. The first construction, it was a machine. Okay, so in the first example I showed you how we can use a model that we know for the world. We assume a model for the world and we try to interpret our data based on the model that we know already. In the second example I showed how we can let the computer create the model. But here in this third example I'll show you how it's also possible to just forget about the models themselves, or at least about complex models. And from very simple principles, try to let the computer find a solution for a problem that we have. So this is another paper that I published with a friend last year, and it's called a mask, so it's a supervised photometric evolution assignment in stable clusters. But the method itself is not restricted neither to photometry and neither to Stallman. You can use the method that is data agnostic, and you can use to any type of cluster. So basically our problem here was a long-standing problem in astronomy. We know that clusters are very interesting objects for many reasons. But to study them first, we need to split or to segregate what are the stars that belong to the cluster, what are the stars that belong to the fuse. Right? This is a very a primary problem. It's one of the first things that we need to do when we are doing analysis. And to do that, we can use positions, distance, parallaxes, motions, and photometry. The point is that each type of observer, they have good things and bad things. Positions, for instance, they are free. You always get a position when you perform an astronomical observation, but you always have lots of contamination due to line of sight effects. Distance are perfect. If you had distance for everything, we would not even have a problem to solve here. The problem is that we don't have distance for everything. In fact, we almost don't have good distance in astronomy. Other things are motions, so proper motions and radial velocities. They are good to perform the segregation, but they are very expensive to measure. Either you need to wait for a long time, either you need to integrate for long times. And photometry, that's just like positions, are rather cheap, but the problem is that you have to make strong assumptions on what you expect from a cluster in order to use photometry to analyze the cluster. So, me and Andrea, we had a question, but would it be possible to let the machine itself try to emerge with what is a cluster and let the machine tell us what's a cluster? So, to do that, we need to at least to teach the machine something. And what we came in the end were the weakest assumptions that we could make about the cluster probably. That is one. Members of the cluster are located in the same region of the space, and the member stars, they share some common characteristics. We are not telling what are the characteristics. We're just saying there will be things in common among those stars, among those objects. This means that the cluster stars may be clustered in several parameter spaces. Meanwhile, the few stars may not. They may be clustered in some parameter spaces, but not in many, or they will be in some and not in others, unless you have special effects like reddening. If you have variable reddening in your line of sight, then in fact you are faking a cluster. Okay, so how does it work? The idea is that from the photometric data, we compute a PCA analysis, and we extract the four principal components, the four most important principal components. Why four? First, because most of the variance is within these four principal components, but another reason is that somehow they should encode, well, we know that photometer should somehow encode the distance, they should somehow encode the age, they should somehow encode the reddening and also the metallicity of the stars that are being observed. We are not saying how they are encoding it, but they are encoded in photometry. So in this principal component space, we use a very simple logarithm, a clustering algorithm that's called k-means, but you can choose any other clustering algorithm as well. And for each one of the clusters that this clustering algorithm defines, mathematical cluster, in the principal component space, we check if the stars are also clustered in the positional space. And to check that, we compare with, we use kernel density estimators to compare with random distributions of the same number of stars. If the clusters, for each of these clusters that was analyzed in the principal component space, if it's compatible with a random distribution, we assign all those stars as field members. If it's not compatible, we assign all the stars as cluster members. And we iterate that loop until there is nothing changing in the lists. Okay, but this gives us a 0 and 1 probability. So it just says that the star is a member or the star is not a member. And there are many things associated with the observational process. You have errors, you have missing data, and we wanted to take all of that into account. How we do this? So basically, we don't use the data, we don't use the average measurements that's in the catalogs. We use random trials, so we create random clusters based on the data itself, so the average value, and on error models. So if you know that your errors are Gaussian, what we are going to do is to create a simulated cluster based on Monte Carlo simulated cluster based on the data and on an error model. And optionally, if you have missing data, you can also add a model for your missing data. For instance, a model that's pretty simple. You don't have the observations in one certain filter for a certain star. But since you can make a reasonable assumption that the star is in the galaxy, so you know it is some bounds where you can try randomly some values and to put that star into some analysis. So you run the agnostic kernel several times, and in the end, you can check for iterations, the number of iterations, or you can check for the convergence into the probabilities. But in the end, what you have, it's a frequencies probability. So if a certain star was assigned as a member of the cluster 80% of the times, or 70% of the times, you can say that it has a 70% or 80% chance of being a member of the cluster. But this is a very raw probability. It's more a frequency of appearance as a member of the cluster. Does it work? So this is a simulated case, just to show you an example. These are positions of stars, and this is a core magnitude diagram. And you have a cluster inside. So these are the simulated cluster that is among all those points. And this is the core magnitude that should be here. I'm sorry for not keeping the same scale. And in this plot, this is what a mask finds if you only use this data. So from this data, it manages to disentangle this cluster. So the size of the points show the probability of being a member of the cluster. But okay, so we have good purity and good completeness. Even visually, you can say that you have pretty good completeness. We use some stars and we have some wrong assignments. But overall, for a method that never learned what was a main sequence or anything like that, he had to learn by himself. It worked. But this is just one case. We run these methods in thousands of different clusters, different ages, different distances, and different masses. And for all of the clusters, we managed to keep the purity above a median level of 75% in the world. This is the purity against the contamination. sun in the cluster and different areas of the cluster. Okay, but this is all simulation. In simulation, things can work pretty well. This is work in real data. So this is a hard case that the cluster is half over 16, and it's hard because we have few stars, and those methods really generally require lots of stars to be able to create them correctly. So this is the positions of the stars, and this is the color magnitude diagram of the stars. So standard physicists would probably see the main sequence coming up here. After we run upmask gives us this color magnitude diagram with color representing the probability of the star being a member or not of the cluster. And there are very interesting things here. Well, the main sequence he managed to disentangle, but he managed to disentangle himself also double stars that belong to the cluster. And something that I think personally that's even more interesting is that he found a signature of the premium sequence of the cluster. And a few weeks after we finished this analysis, a paper came out in AstroPH showing the premium sequence. But it was an astronomer who looked into the data who found the premium sequence. And here, the machine found itself the premium sequence and showed, hey, here, there's something interesting. Take a look at this. So basically, this is the summary of what I wanted to talk about today. So the so-called fourth paradigm or data-intensive science emerges in astronomy as the discipline of astroinformatics, astrostatistics, and the virtual observatory. And that by embracing this paradigm, we can profit from data that was created for a reason, like Gaia, for instance, that was created to study stars. And perhaps study more things than just the data that it was the main objective. We can also perhaps begin to entrust some higher level tasks to machines during the discovery process, like proposing analytical representations of the data. And in certain cases, we can even let the data tell us more about itself than we are used to, more comfortable with in general. And we can have a good surprise at the end, like the primary sequence that I showed. So these approaches are central to, this is a very personal opinion, to make sense of large surveys like Gaia, Euclid, and LSST, for instance. But not embracing this type of approach also in smaller scale studies, it's probably to waste information. And we are seeing that in a parallax program that we are running at ESO for brown dwarfs. If we were to, sorry, not an ESO, it's a solar telescope. It's also cheap, but it's not. For the ultra cool brown dwarfs that have between around 350 Kelvin of effective temperature. And we are able, using data denoising procedures, we are able to cut by half the telescope time that is needed to attain the same astrometric accuracy. So, thank you very much. Just 3 minutes more to present something. Okay, so now a little bit of sense for the next episodes. One interesting thing is that these concepts, this type of concepts, they might also affect not only how we analyze the data, but also how we measure the data itself. I've told you about, just commented about the lowering the needed telescope time to attain a certain objective, but we can even change how we build the instruments themselves. There was a series of papers, seminal papers in the IEEE Transactions of Information Theory in 2006 that showed that if you have a signal, if you're measuring a signal that is sparse in some places, you can reconstruct the signals from very, very few measurements of the signal. You don't need to completely sample the signal to reconstruct it. And the nice thing here is this word, to reconstruct signal exactly. This is the basis of something that's called compressive sensing or compressed sensing. And basically the idea is that you are not going to measure the signal, but you're going to measure projections of your signal over some random basis. And then you're going to solve an optimization problem to reconstruct the signal. And it's very interesting because using this concept, we can make possible to create instruments that were either feasible or even, in some cases, impossible before, like single pixel cameras. So it's a camera that you are only going to use one pixel, and you're not going to do raster. You're going to integrate the signal in different bases. Or, and this is very useful, for instance, for the infrared region, where the detectors are very expensive, or for the far infrared regions, where we have nowadays 64 by 64 detectors, if you're very lucky. Using compressive sensing, we can have probably a 2K by 2K detector in the far infrared as well. And also, one very interesting concept is the hyperspectral imagers. We can create very compact integral field unities. I will show you an example. And 3D cameras, tomographers, and lidars. So this is just an example of an integral field unity. So you know all those very big instruments that needs all the fibers, one places just after the other. This is an IFU that has the size, about the size. So it could fly into a space mission. But this is really a full-blown IFU. And the spectral resolution is only set by the diffraction rating and by the center, not by any other type of constraint. So this is a very recent design, it was from 2014. This is one example of this IFU observing the scene of a toy. And for each pixel of this toy, you have the full spectral distribution, and you can reconstruct all the different images. So even with something that's that small, we can already do things like IFUs. And you can hear the resolution of this one, it's some nanometers. But we can go to the 7 nanometer level by changing just the diffraction rating and the center. And the rest of the instrument is just the same. And in this one, we are creating, this has been applied to other fields, but in astronomy there is still no application except for data compression purposes and for data analysis as well. In the Herschel telescope, they tried, in the Herschel space mission, the CAR team in France, they tried to use that in Herschel and showed that they had a very good data compression rates. So this is an example that we're building. It's a single pixel camera to work in the infrared domain. This is an example of the simulator of the system, observing a galaxy. And these are the different reconstructions depending on how we're sampling the signal for something more or less. And I hope that at exactly this moment, there are 2 master students that they are working on implementing the physical prototype. We have the software running, the simulators running, the design is done, and they are now creating the physical prototype. And the nice thing is that they are using 3D printed optomechanics that they are printing in-house. So perhaps in a few years, you all will be able to just print a single pixel astronomical camera to fit in your telescope. Okay, so now the mission.
It's a tradition that the priority for the first questions is given to the students. So are there any students who want to ask questions?
Yeah. Is it fair to call it the fourth paradigm science? It looks all very impressive, but in the end what you're doing is finding empirical correlation. So it's still empirical.
Yeah, in fact, it's not empirical because it's not really going back to the empirism. But because you still have the theory, the idea of the fourth paradigm is that you have the theory and the data, and you must make the two things fit themselves. It's just that to make the data fit with to make the theory fit with the data, the theory is so complex that you cannot explain the theory in simple with correlations anymore, and then you need to produce data. So in the end, you have data with data. It's a type of empirism, but it's not pure empirism, because pure empirism would be just look into the nature. But here, it's not only look into the nature, it's look into the nature and also creating words. It's just that sometimes you can create a word, or you can let the computer create a word. But this is the difference between pure empirism and this.
More questions, please. That is not the case. It's open for other questions.
I think that was a very nice talk. Thanks a lot. But I'm wondering, and I think my question is very similar to the previous question about your third example. In principle, you have shown us an algorithm that can extract clustering from looking at hidden correlations in the data. Then you get a color magnitude diagram or luminosity temperature diagram. But then you look at it and say, oh, this must be binders. Oh, this must be premium sequence. So I don't really see, except a fantastic new clustering algorithm, how on the interpretation side the machine is helping. Because again, you said, oh, this looks strange to me, let me look in my textbook, let me speak with my colleague, why is this strange? And then you come up with an interpretation.
The point is that we still didn't arrive at the point where the machine will do the interpretation. The machine is helping us to do the interpretation each time more, but at least until now, we are still doing the last part of the discovery process. Because perhaps someday the machine will write a paper, right? But we are still far away from that. We are still at the moment where the machine is selecting what we should look at. This example of the cluster, for instance, it's just that the machine is indicating me what is interesting. If I had to look all the clusters and everything and myself searching, it will probably be impossible for a survey like an SST or Gaia. But the machine can indicate me what's interesting inside those surveys. And this is a little bit of a paradigm shift. And it's not only that it's a natural paradigm shift. We are not breaking anything, but we are doing science in a different way that we use it to do. Well, not my generation, but my generation were born inside this paradigm, and we are evolving and living for this. But it's a little bit different from what I've been doing before, only because of the volume of the things.
Well, I'm skeptical about the paradigm, I must say. And as I see your last example, you have, because you have these enormous data volumes, to come up with a better way of identifying things. But then again, the interpretation and whether you finally take objects and assign meaning to them, that is left to you. So I don't really see a change in the way you do science, except that the pre-selection process has been done in a more smart and more big data framework.
Yeah, in this case, yes, but for instance, in the second case where the machine invokes the equation, ignoring the filters that were not important for what she was looking at, what the machine was looking at, this is, I think it's a counterexample.
That was partially also an example where you later saw that if you include the higher Z values, that the system ignored it by itself because it looked where the majority of the measurements were. So it could also fool you.
Yeah, of course. But in the same way, the machine, she was working with its local data. if you had fed the machine with, well, the machine wrote that equation, and then she starts applying that equation to LSST data, and she will see, oh, it's not working anymore. What should I do? Why it's not working? Oh, now I should have included this filter. Why? Well, the point is that we are still not in that step where the machine can connect different fields or different data sets. There's still missing this connection of knowledge in a larger scale. But this is something that's also happening, for instance, with the virtual observatory. The standards are being created for those things.
So I had a question or a remark actually about the second point, so it's good that we're now already discussing it. Because I think analytic expressions are a language that we use to communicate something that other people can use to understand something. And when I was looking at your equation, even though it was very complex, I was trying to figure out actually what it means to me. The lower to the power 2 of 2 ratios of fluxes. And I didn't really understand. So you have an equation which says
Just put the equation so everybody can.
so if you actually try to figure out what it means in terms of, so you have G minus R, because those are lower fluxes, right? And then you have a G at the end of it.
Yeah, so we did not try to interpret.
So to me, this is a pretty way of describing fitting line.
Yeah, it would be a fitting line if we had provided the equation, right? Because this is, in a certain way, it could be as a fitting, but it's a much more complex fitting. Because you can have the entire mathematical space for this system to work, and it could have written an equation with logarithms, for instance, or with exponential sinuses that would perhaps predict the data much better. But those equations were more complex. And then you have the trade-off between the complexity, and this is the beauty of this symbolic regression. You have the trade-off between how good it is to fit the data, and also how complex it is, or how complicated it is. If you have two equations, one is very complex and fits out the entire data, including the noise. Another is simpler, but it's perhaps not, it fits not as good as the other one, but it's under a certain error. The method will choose the simplest one.
I think there's a beauty in the compactness of it, but I still don't think that this is something you could give to Newton that figure out how the planets are. I mean, that's the point.
Yeah.
We've used it as a language to communicate some ideas, and maybe you should call it numerical analytics or something. I mean, maybe you should give it a different term, because it's not exactly the same concept.
For instance, it's not, but there are other things, because when a human being is looking into an equation, he's trying to connect all the knowledge he has already from physics or from mathematics. But perhaps this is just another step that we need to take. For instance, here, in this method, what the method does, is to randomly create candidate solutions. So it's a genetic algorithm, but it's pure genetic algorithm. Just not a generic, it's an evolutive method, but it's pure. Perhaps you could, for instance, add an algebraic engine here, and as the first candidates, you could add only the known laws of physics, and you could let the system try to derive the equations, not to just keep randomly mathematical terms. That would be another approach. And then you would keep the connection with what we know already. Because when a human being is writing down the equation, we are doing that. We try to part from the first principles.
Are there more questions? If this is not the case, I thank the speaker for the interesting talk and everyone for the very interesting and controversial discussion.